Cool. Thank you very much, everyone, for joining. Hi, my name is Aki. This is the second protocol community group meeting. The last one took place 3 weeks or 4 weeks ago, roughly that time period. For those of you who are new, this is a community group for people who are interested in the NEAR protocol, adding features to it, following developments to it, just interested in extending the NEAR protocol and contributing to it in various ways. So the format is fairly straightforward. It's a free-fall discussion. We're not taking any decisions here and so on. Ori and I are hosting the call, but we're not by any means. We're just here to facilitate discussion and encourage people to contribute and just moderate a bit. And we will also be taking notes, and we will try to summarize the meeting offline afterwards. And I believe this meeting is being recorded, so please keep that in mind if you want to share something that is security sensitive and so on. All right, is there anything else I should add, Ori, or do you want to add something?
No, I'm just excited to be here and see everyone, and we have quite a bit of new topics. So
cool, yeah. So last time we had done introductions where people talked about who they are and where they're from, but we got feedback that took a bit long to do. So maybe if somebody's want to say a few things about themselves, maybe please use the chat to do that so that people can read that offline. And I would love to see people do that. But in the meantime, we can let's get started. And so these are the proposed topics that we have. And this is just based on what people have proposed offline on various forums. And before we dive into them, is there any? Does anybody have a strong feeling on any particular topic that they want to discuss first, or in the order of the topics here, or should we just take the discuss them in the order that it's listed there? Right, I don't see any comments, so we can just take them in the current order then. So Garvit, why don't you start us up then? Maybe you can start us off by introducing yourself a little bit too.
Yeah, absolutely. So hi, I'm Garvit. I'm from Electron Labs. And so we have been building in the NEAR ecosystem for more than a year now. And I think our core contributions have been around ZK technology. And one of the coolest things that we've built so far is a ZK light client for NEAR. And going forward, we are building basically a decentralized bridge between Ethereum and NEAR. That is actually already live on testnet. And it's basically a bridge very similar to the Rainbow design, that it's powered by light clients, except that we're not running these light clients directly on chain, but rather than creating ZK proofs of these light clients, which means that our light client verification on chain is around 200 times cheaper, which allows us to follow a validity proofs approach as opposed to Rainbow. So Rainbow takes like 16 hours for a transaction to go from NEAR to Ethereum. While using our approach, it takes us a couple of minutes because we can submit proof directly for each header, right? So yeah, gearing for mainnet as we speak. And while building the ZK technology for this bridge, we realized that it has a lot more applications than just light clients and scaling in general. And that is when the discussion with on the protocol group, I posted some questions that if this can be actually used to scale the number of shards that NEAR can handle at this point. And what I'll be presenting today is along those lines only. I'll not be presenting I don't have any concrete ideas to present today that, this is exactly how we can scale. But the purpose of this presentation will be sort of educational and just triggering some thoughts, maybe hopefully from some of the core team, that how to apply ZK, where does it currently stand, and what is the roadmap in terms of ZK technology itself going forward. So I'll just summarize those things. So I'll just try to share my screen at this point. Can you guys see my screen?
Yeah.
Great.
By
Okay,
the
so
way, by the way, Garvit, do you have a link to this that we can share with everyone later?
I will post a link to it. I don't have immediately, but I will.
Okay, thank you.
Great. Yeah, so I'll just get started, right? So I'll be talking in context of some of the work we're already doing, because then we can actually talk about what we've done and show some numbers around. Yeah, so basically, what we've done so far is basically create a ZK proof of the near light client. So that essentially has three parts, computationally speaking. One is the header fields, such as tracking of the voting power of each validator, for example. The second part, which is the computationally most expensive part, is the signatures of the validators themselves, the ED25519 signature scheme. And finally, we have the transaction Merkle proof, which allows us to map a particular transaction to a given header. And in the current design, what we've done is we've created a ZK prover for the signature scheme itself. So we can take in a batch of 100 validator signatures and create a succinct proof of that. And if you want to verify these proofs directly on chain, it will cost you millions of gas and thousands of dollars on a per transaction basis. But in our case, we are able to verify these signatures for 227K gas, right? And add to that some of the overhead of the headers and the Merkle proofs, we can actually verify a single transaction and an entire header for 1.1 million gas. And these are actual numbers from an actual implementation that is live on testnet today for the bridge that we have done. In terms of gas cost, in transaction cost, it basically means $31 today. And if you were to compare that with, let's say, without using ZK compression, we are achieving around 50x scalability, assuming that we only have 100 validators. As the number of validator grows on near, we basically give you around 200x scalability using the ZK approach, as opposed to a non-ZK approach where you're directly doing this on chain. And this is basically a comparison with the current Rainbow based design also, because Rainbow is doing this directly on chain as of today, right? So these are actual numbers. This is not futuristic number. This is actual implementation number that we have tested. Now, if you talk about a bit more about this approach, this has a couple of limitations because it's using Groth16 as a system, which means that it takes a lot of time to generate these proofs. For a full validator set, we can take up to 16 minutes. And we can only prove up to around 100 signatures. As the number of validators on near grows, we'll not be able to prove them, and we just have to create more and more proofs, right? And this is because with Groth16, if you go above a certain amount of computation being proven, it gets computationally more and more unfeasible to do it. So we kind of hit that limit here, and we can't really go above 200x scalability as of today. So this is currently the implementation that we have that is live right now in our bridge. Now, of course, these are quite a few limitations, and if we are saying that we are infinitely scaling here, we have to do a lot better than this. And that is where some of our future roadmap comes in, something that we are researching right now and planning to start dev on this very soon. So this is the concept of recursive proofs, something that Mina protocol does today, or if you might have heard about Plonky 2, for example, or this is being done by ZK EVMs also today. So proof recursion is a very simple concept that you can actually create a proof that a given proof is actually valid, right? So it's a proof, ZK proof of a proof, and it's quite trivial for a single proof, but it starts to become powerful when you start combining these multiple proofs together. So you can create a proof that multiple proofs given to you are actually valid, right? And it gets really powerful when you actually scale this out. So you can basically supply a large number of proofs on the left side and successfully recursively combine them together and create a single aggregate proof. So this single proof on the right is proving all these proofs on this left side, and every single one of these proofs could have a large amount of computation being proven. So every single one of these proofs could be, for example, a single header, a light client header, and then this single proof is proving, let's say, last 12 headers in a single proof, right? And the advantages of this approach is, as you can see, that you can basically take advantage of parallelization here. you can virtually have these millions of proofs being generated in parallel and then being combined together in a single proof, right? The big best property here is that the limit of parallelization here is the limit of number of machines you can get together together in a single instance. And this basically now scales, the proving time now scales logarithmically now, right? So the more computation you have, you basically, so if you talk about Plonky 2, for example, which is the state of the art when it comes to recursive technology, within 1 minute, you can prove trillions of constraints, right? And if you just go back a couple of slides, over here, we were proving 256 million constraints in 16 minutes. But now with Plonky 2, you can prove trillions of constraints, and actually not just virtually infinite constraints with an upper limit of 1 minute. It doesn't really go above that because we have log scaling now. And with 1 minute, I think there's a theoretical roadmap that is also people are working on. This is slightly theoretical, but people are working on hardware acceleration and even advanced schemes compared to Plonky 2. Which will bring down the cost of proof generation to single digit seconds for very large amount of computes. Now, once you have this kind of a technology, and if you zoom out a bit, you basically essentially have here is a computational compression engine, which can take massive amounts of proofs or computation that needs to be proven and reduce it down to a very small amount of computational verification cost, right? And ZK generally works with computational compression only. That's the whole idea behind it. But if you apply it a bit smartly, you can actually reduce the data and the network requirements also quite significantly, as we'll see in certain cases, right? So I believe that, like, so at this point, no one really has this in the market in terms of a generalized engine. And I think this is a massive opportunity for us to actually grasp to build this, right? And let's get to straight away the use cases for it. So the first use case is actually one that we are also building for ourselves. So what you can do here is you can create a single proof that proves the entire consensus of the near blockchain since Genesis. So you download a single proof and that's it. You have the entire chain being proven to you, right? So this removes the need to have any trusted RPC clients. You can actually run a light client or actually almost a full node inside a browser or the client side. And this basically enables trustless bridging where the cost of the bridge and the overall performance of the bridge is very close to what centralized bridges offer today, right? And just to add here, as a side note, this is again very much for the future, that if you can somehow create ZK proofs of the VM execution also, the Rust VM that we have, we can actually turn near blockchain into a constant size blockchain where a single proof is essentially proving the entire history of transactions, right? But yeah, this is quite theoretical, something beyond our scope, at least at this point. But yeah, at least the ultralight client thing that we've already started to research on. And this is one more slide I just added just to kind of summarize some of the thoughts I had a chance to discuss with Aki on the protocol working group and Boven also on the Zulip chat. So some ideas that I want to mention here that can actually help scale. So the first one is something very similar to how rollups work, where a single transaction, right, can be replaced with a proof, and you don't actually have to do any consensus changes here. You can simply put the ZK proof inside the transaction, and this proof is actually proving a large number of other transactions, right? So you basically get this virtually infinite computational space inside a single near block, right? So without increasing the number of shards, we're able to increase the computational block space that we have available. We'll have to obviously think about how the data requirements change here, but at least we get rid of the computational overhead. Another idea is that we can actually build constant size block headers with respect to the number of validators. So as the number of validators grows on near and gets to, let's say, millions of validators, we will have these very large block headers, which can become increasingly costly to share around across shards. And we can actually simply create a proof of validity for all the validators and actually not have to add any of these validators inside the block header. Similarly, this can be extended to improving inter-shard communication, reducing the data requirements inside it. Again, I'm still very much a noob in terms of Nightshade and the consensus, and I'm not sure what data is being sent across. But if some of the data is being sent across to verify something on the other side, I think this kind of concept can really help. Yeah, and I think Ilya also mentioned quite a while back, around 6-7 months back, that he does believe that ZK has some potential there, although I'm quite not sure at this point how that will work. And that is where actually the protocol working group can come in. Yeah, so we have already started to design the circuits for how the light client will essentially fit inside Plonky 2. And we are planning to start the dev on this very soon, probably this weekend. We already have some internal papers that we've built. And yeah, that's pretty much it. And just wanted to mention again that our bridge is live, which uses the current Circom implementation, not the Plonky 2 one. And yeah, that's all I had to present today.
Thank you very much for the presentation, Garvit. That was very informative. Does anybody have any questions for Garvit, or any comments in general on the?
It looks like Bowen typed one question in.
Oh no, I think it already answered it. Yeah, I mean,
okay.
I was going to ask the exact question of why not using Plonky 2, but yeah, it's already answered in the presentation. So I mean, yeah, I think Gross 16 is more like a. I mean, technology move very fast, right? It's now already considered like a older generation of proof system, I think.
Yes. Yeah, precisely.
Yeah. But yeah, also on the point of scalability, yeah, I think this definitely is the future. So I think with ZK, so I mean, if like the bottleneck of the system is purely execution, then there's not much ZK can help, because like someone still have to do the execution, even with all the ZK proofs. But I don't think that is a bottleneck per se for us, right? So I think for us, the major bottleneck in the future will be communication overhead, and also kind of the verification overhead. And I think in both cases, yeah, the key proof is definitely the way to go in terms of resolving those bottlenecks.
Yeah.
So when do you think we might start hitting those kind of bottlenecks, Bowen, or when do we need such technology implemented?
Yeah, so I mean, the short answer is I don't know. And the long answer is I think with the current design can maybe scale to 100 shards, I hope. But I think, if you ask a question of how do we get to 10,000 shards, I'm pretty sure that we will hit some like bottleneck somewhere. And I think that's where, like, if we have, if we get to the kind of holy grail design where each shard is pretty much like a ZK rollup, then yeah, I definitely think it's possible for us to scale to something like 10,000 shards. But yeah, I think the main problem there is like there is a long way to go to actually get ZK Wasm to work, right? My understanding is that there are people working on it, but actually making sure that things work properly, and it's I mean, I think it's still like in the early stage of research and implementation.
When you say ZK Wasm, do you mean proving whatever transaction the smart contract executed, or?
Yes. Basically, the end goal is that there is a proof for the entire state transition.
Right.
So, Bowen, I had a question here, right? So, when it comes to inter-shard communication, would I be correct if I said that from one shard to the other, you're essentially sending a light client proof of the first shard to the second shard while you're doing this cross shard communication? Would that be like a correct assessment, or?
I think partially, yeah. I think for everything you need to prove, that's kind of true. But what the main problem there is that there is a lot of like a data communication overhead, right? Let's say you want to, for example, I think the cross shard part is is okay, but let's say you want you want validators to rotate and rotate into some shard, right? It's that means they need to download all the data. They need to, let's say, they need the state to actually verify that to actually execute some block or chunks, and then that overhead is pretty big, right? And then for the cross shard communication, that's mostly just sending kind of receipts between different shards. I mean, yes, that is also potentially going to get pretty big with the number of shards.
Okay. So yeah, I think like if downloading the state is the limitation, yeah, I think, yeah, I'm not sure how ZK could help you there. Maybe there's some way, but yeah, again, I don't understand actually.
No, I think, yeah. So where ZK would help is you don't need to download state, right? Like if there is a proof for the entire state transition, then like every validator, they just need to validate the proof, because today the reason why they need to download state is because they need to validate the shard, and then they need state to actually do that. But you know, with ZK proofs, that's not really necessary.
Got it.
Okay.
But I think yeah, we're talking about like not what's going to happen this year, or maybe even next year. Probably we're talking about what's going to happen like a couple of years down the line.
Cool. I know that there are other topics on the agenda, but I guess just to wrap up, I guess, yeah, is there any next step or request like for Garvit or the community now that we've talked about this?
Yeah, so from our side, actually, we are discussing this very actively in the ZK working group. So I do have some requests to make, but I think that would be the right platform to do that. For this working group, I think the goal was to just kind of introduce this idea that this kind of technology, where does it stand today? And so that people thinking about protocol can start thinking about it. That's all, I think. Yeah.
Yeah, and for me personally, I actually don't know a lot about this technology. It's still pretty new to me. And so the more I'm getting introduced to it, the more I'm learning about it. And then I would love to find more nails that I can use this hammer with, you know, and I'm sure we'll find more use cases for it. So yeah, thank you very much, Garrett. And yeah, I'm very happy to see your involvement here. Is there any other comments for Garrett before we move on to the next next topic? All right. So I think the next one up is Min, who wanted to show some solutions for the congestion, or propose solutions for the congestion problem. Min, are you around? And
yeah, I'm here. Okay, so I guess I'll propose, sorry, I'll share my screen. Can you see my screen?
yeah.
Yes.
Okay, so this is like a short design doc I wrote for the, like, I guess, part of the solution that will affect developer experience the most for the congestion problem. I will share the link of this doc later, and please feel free to comment in the doc, like if you have any afterthoughts. So like, to be honest, the design is not completely finished yet. There's still some unsolved issues. I actually just realized some new issues this week. So really the kind of like the goal of this presentation or discussion is to kind of gather more input, like different viewpoints from like everybody from the community, to see what are the, you know, potential impacts, and so we can work on fix those. So as a context to what is the congestion problem? So basically, we are worried that once NEAR gets very popular, the blockchain will start to accept a lot more transactions than it can handle. What will happen then is the transaction will actually be queued up in the system. They will be accepted, but it will take a long time for them to process. Like, so right now, once the transaction is accepted, it's like, it gets processed very fast. But if the blockchain gets very popular, it's possible that that delay will increase. And in the worst case, actually, the delay is unbounded. And we definitely do not want that to happen. So let's just consider like an example. So let's say that we have a near social contract, which is very popular. And the near social contract sits in one shard. And users can actually submit transactions that call near social from any shard. So it's possible that just like in one block, this near social accepts, the shard of near social actually accepts more computation load than that block can handle. So let's say if I submit like every shard submit like full block of transactions to near social, and then all those load will actually need to be handled by the shard that where near social sit at. So that shard will actually, all those transactions will just be queued up in the system. And then a backlog will start to actually form in the near social shard. And if the traffic keeps coming in, this backlog will only just grow longer and longer. So it will, like, the new transactions will actually take longer and longer to be processed. And as I said, in the worst case, the latency is actually unbounded. And that basically makes near social unusable. So solutions, what are the solutions to this? We are considering multiple different approaches to the problem. A few of them actually both require the protocol to kind of break the guarantee that we provide today to cross-contract calls. So today, if the developer attach enough gas to a cross-contract call, we actually guarantee that the cross-contract call will succeed. We actually think that this is almost too strong of a guarantee that protocol provides. So today, actually, everybody, if you submit a function call, everybody just attach 300 teragas, where it's actually like the transaction, the protocol actually doesn't know at all how much this transaction will actually spend. Furthermore, actually, it doesn't know which contract this gas will be spent. I can submit a transaction from min.near, but eventually it could go to social.near, which could go to another contract. So this all kind of leads to the problem that the protocol can't efficiently limit the input to the system. That's like the source of why the protocol could potentially accept more computation load than it can handle. So one solution we want to propose is that to break this guarantee, which means that we no longer guarantee that a cross-contract call will always succeed if you attach enough gas. Obviously we understand that this is a very big decision and impacts everybody in the ecosystem. So we want to make this transition as smooth as possible, which kind of lead to the two options we want to provide to contract developers regarding to how their cross-contract costs will be handled. And so the first option is that, so basically it's very similar to what you have today, except that basically you have to write callbacks. Like right today, I think a lot of the contracts already write callbacks for cross-contract costs to handle the failure cases. So if you choose this option, since in the future, like any cross-contract call can fail, so it's actually required that people write callbacks to handle the failure. And this option, we actually guarantee that, like, no cross-contract call, we don't provide any guarantee for cross-contract calls, but we actually do guarantee that callbacks would be executed. So as long as you write your callbacks that handles the failure cases of cross-contract calls, the contract will actually be okay. The second option is that if a cross-contract call fail, we actually don't drop the transaction immediately. We simply just pause the transaction, and the system, the Oracle, will actually store the intermediate receipts so that the transaction can be resumed by the user later. The kind of main difference of this approach from today is that somebody needs to pay for the storage of these receipts because they'll be stored by the system. So in this proposal, we ask that the contracts pay for the storage for receipt they create, because we don't want to increase the upfront costs for transactions. If we ask users to pay for it, then we actually increase the upfront cost for all transactions, which is undesirable. However, because then we basically ask contracts to pay for this, and the contracts will have to put a certain amount of money in their contracts to cover like the temporary stake for storing receipts. The stake for these receipts will be refunded to the contracts after the receipts are executed. So these storage is actually, the stake is only charged temporarily. So if you put, let's say, for most contracts, we estimate that 15 years will be enough to cover the storage for its traffic. Yeah, so this is basically the solutions that we're thinking about. The questions we'd like to ask to the community is that, so basically we want to have a better understanding of how people handle, like how people view about cross-contracts calls today. Like, do you actually write callbacks? Or like how often do people just not write any callbacks and just assume that we always attach a lot of gas to transactions and just assume that running out of gas never really happens. Is there any questions?
Any feedback or questions from Min? Yeah, Alexander.
Yeah, I have something. I would say that the first perception when you're talking about cross-contract calls. It kind of ring a bell because as a developer of smart contracts, cross-contract callbacks are most, I would say, painful and not really cool part from perspective of development experience. I remember we have a topic of developer experience in this meeting. And so I don't think we always implement callbacks for the cross-contract calls, but probably in the end of the day, we had to create many callbacks, and many of them are implemented in a style of some like implicit tradition or implicit requirement just because of different feedbacks from fellow developers and security audits that you don't handle this situation, you don't handle this situation. So the second part of my message is that proper handling and proper implementation of callbacks also introduces or not, but it usually introduces security issues and security problems, kind of almost always when we get some security feedback from security audit, it lays somewhere in the callback implementation. So I don't say that what you say is completely is a bad idea, but if you want to introduce option 1 where developer needs to trick with cross-contract callbacks, callback handlers, then it's probably better to introduce it somewhere deeper in the near SDK, so developer don't touch it for sure. And it introduces backward compatibility issues, so we have to merge contracts to the new SDK. But if we face with the real congestion problem, then we just don't have choice. But anyways, keep in mind that callbacks and callbacks are kind of painful part in all this development experience.
Yeah, that makes a lot of sense. Okay. So what do you do today about your cross-contract calls then?
I just, accept the reality. I mean, could you specify your question beside of this? Could you please? What do you mean? What with cross-contract? I mean, like we just developed because we have to handle some business level cases. I would say, it's not that like we are forced to create cross-contract, cross-contract callbacks handlers. I would say that for people who who never developed contracts for a near protocol, that handler is a function which is called when the cross-contract call has been ended, and it's usually is executed in the context of the next block. So it's not synchronous. I mean, yeah.
Yeah, I see. I think we can implement something in the SDK level, but like the specific logic of callbacks will still have to be determined by the contract because the SDK won't know what to do.
Yeah.
When it fails.
Yeah, we usually have to create conditions like if the previous transaction, previous function was failed, then do this, else do something else. And it's literally, I have to copy paste code from my old contracts. Like if promise is not succeeded, like do that. It's already like kind of complicated. So if I have to add another condition, I will fail for almost sure. And let's think about junior developers. I think they struggle with it.
What if I don't know if it's possible or not. This is not my space, but what if we had some sort of static analysis tools that could evaluate your contract and highlight such issues, right? You could build your contract and run it through this tool, and it would try to give you some warnings. I don't know if that is possible or not. I mean, how difficult it would be to build such a tool, but that could be something that could help maybe. Or what do you think, Alexander?
As a quick question, I would say there are two cases. One is ideal and another is not ideal. I mean, the perfect case is that SDK has to provide, means to develop contracts safely, and that's it. The model should be safe, like Rust. So Rust without unsafe is developed in such a way that it's like 99% is safe, and you expect there are no side effects. And such a tool, which you mentioned, it would be like just a workaround. I feel, but maybe if we don't have choice, it would be my second choice. And now we can use ChatGPT. Just drop there is my contract, and you get the security vulnerabilities. That's it. We already have this tool.
We have the tool already. We have it. Yeah.
We have it. Christian, have some question I see in the Zoom. Christian raises his hand.
Christian?
All right, maybe it's a mistake.
Yeah, Michael made a comment that maybe there can be some macro magic to convert async await into callbacks under the hood. Yeah, that's also a good, interesting idea. I mean, that is what is happening with the Rust ecosystem, right? When you're using async await in Rust, right? Effectively,
when you use async await, it converts it into these poll calls in the background, and so we could maybe do something similar.
So so go on.
I was just going to say this I think sort of avoids some of the pitfalls that Alexander was talking about, because the async await usually leads people to write this nice imperative code that's relatively easy to follow, that usually doesn't do something too horribly wrong, and then as long as the macros are robust, then you sort of offload that complexity from the developer, and they just get to live in this nice world where they sort of read their code line by line, and it's like, oh yes, I do this cross-contract call, await for it to finish, and then check the result, make sure it's all good, etc. Do whatever logic I want with it afterwards. And then, of course, in the case that there is no handling you want to do afterwards, the SDK could automatically always return a result object, so that at the very least, the Rust compiler is warning you about an unhandled result if we were talking about this, requirement to have callbacks always. Something like this. I think it'd be tricky to get it to work properly, but it might be, a good future direction to go in.
So we actually have an example of this from another blockchain where async await. So the Internet Computer uses async await for doing cross-contract calls. So whenever you want to do, whenever your contract calls another one, the Rust SDK or the SDK provides an async framework for doing that. So you call the other smart contract, and then when you call await on it, you essentially return, you yield, and you return out of the function. And when the response comes back from the other contract, whether it's a success or failure, then your contract is restarted and continues from that point onwards. And it relies on the Rust ecosystem, like the functionality that Rust is providing to build all of that out. So I was trying to find an example of that online, but I couldn't find one quickly. But maybe later on I can post something on Telegram.
Cool. Yeah, that's really neat. Yeah, I think that kind of thing would be really nice to see in the near ecosystem as well. Of course, it's equivalent to the callbacks thing, right? It's just the async await is a little bit easier for developers to parse.
Yeah, and it doesn't have these pitfalls that Alexander's talking about. That it forces you to effectively forces you to have the callback then.
So yeah, and I think to summarize, it depends on how you introduce this workaround or feature. I mean, if we solve the problem of congestion, if we're talking about option 1, so it depends on how we introduce this change. And it would be nice to see some more easy, natural way to, you know, handle it.
Yeah, so like we're not saying we're definitely gonna we're only gonna introduce option 1 or option 2. Like we could potentially give you the option of you choose which option you want. So the drawback option 2 is like the contracts will need to pay for a bit more money for the storage of receipts, or this money will be passed to the users, but it's like temporary money, but still you have to put a little bit more money in your contract.
Mm-hmm. I feel like the option, I'm sorry taking the time, maybe we have to switch to another topic, but just as a final note from my side about option 2 is that it seems more tricky, and I feel like advantage, yeah, if, you know, playing with gas is always at some bad experience, just keeping in mind.
What do you mean by playing with gas?
I'm sorry. I mean that if the option 2 is around some gas calculations, maybe I have to dig more into the option 2, but it just feels more tricky. Yeah.
Option 2 increases the amount of storage staking that you need to do, right? So you need to stake more tokens.
Yeah, it's not about gas. It's about you need to.
Oh,
yeah.
Sorry. Okay.
Yeah.
I see someone else has a hand up. I just noticed that. Not sure who the. Bowen. Yes. Yeah.
Yeah, I thought we have a solution that doesn't require us to drop receipt, right? Is there some problem with the solution?
You mean the solution that you proposed?
I think it's Robin, right, who proposed the solution.
Yeah, Robin's solution also requires dropping receipt. It doesn't, the system doesn't drop receipts directly, but if the simulation is wrong, the receipt will fail. It's gonna happen less likely, but we still need to handle that.
If the simulation is wrong. Well, but that's not dropping receipt, right? So in that case, receipt would fail because you run out of gas, right? That's similar to how it failed today.
Yes, but what happens today is that you just always attach enough gas. Like at least you have an option of doing that. But like if you have like the simulation, then like it's kind of out of developers' control.
I'm sorry. I think maybe we're going a bit too deep into this, and I wonder if we should maybe move on to a different topic because I don't think everybody in the call knows what Robin's proposed solution is. So
yeah, okay, sounds good.
Yeah. Well, before we move on though, I mean, does anybody have any more feedback for Min? Any other comments for her?
Is there a place I can share this doc? Like, do you have a Telegram
Yeah,
channel? where
yeah, there's a
everyone-
Telegram group. Yeah, yeah.
Okay.
You can ping me offline and I can send you the link and so on.
Okay, thank you.
All right, cool. Thank you, Min. So we don't have a lot of time left, but I think we had great discussions so far. So I'm happy that we did that. Orange Joe or Joe, do you think we can discuss the development experience in the next, say, 5 minutes or so, or do you think we'll need more time? I mean, we can start the discussion and we can continue it next time too.
Yeah, sure. We could start. I have a little different perspective than Alexander's maybe, so I can just kind of give some feedback and then next call we can go more into it. Sure.
Sounds good.
Yeah. So I'll give a quick overview and then I'll kind of dive into. So I come from a very heavy Web2 background before going into crypto. I built a lot of platforms, like SaaS-based platforms, really heavy into API-driven type of work. When I started building on Near a little over a year ago, what really attracted me to it is, before even getting into the smart contracts, is actually how impressive the API SDK is. And that was actually what kind of hooked me at first. And so I think it's a really, and where there's such a push for, like, hey, anyone who knows JavaScript can kind of come into the ecosystem. For myself, that was building a lot of, backend systems, to be able to have a really robust API SDK really kind of hooked me, like, oh, okay, I can do a lot of really interesting stuff here. And then as I transitioned into building actually smart contracts, that transition actually was easier than when I tried on other chains. So I did like the whole thing that I think everyone kind of did for a while, right? I tried out Solidity. I tried to build something on ETH. You could do all the basic stuff and then go a little bit more complex. It was not as intuitive for me, so I kind of backed off. I've had a job in the past year too where I've been building on some other chains, did some work on Sana, I did some work on Aptos. And when I compare the work I did there to the stuff I do on Near, it's really like a breath of fresh air to build back on Near. It is really so much easier and more straightforward. Even it's like where I know as a pro, we're working out a lot of the kinks of, like, the call discussion just now, right? Those are things that we're still kind of working out. But anyone who has started to develop on some of these chains and having to go through that process of, understanding what's required, understanding the nuances on there are still much smaller, and really start to run into that and to do more stuff where you can certainly build an introspection before you or like solve it. Really allowed me to get a better sense. Well, I think my audio cut.
Yeah, it was a bit choppy at a moment. Yeah.
Hold on, I think I lost it a little bit.
Hey, Joe, I think, we're almost at time, but I would love to continue this in our next call. Is that okay?
Totally, absolutely. That sounds great.
Okay. Do we all want to meet in 2 weeks again? Okay, cool. So we will go ahead and schedule in 2 weeks. So thank you all very much.